Hello everyone, and welcome to Demo Fleets Unlocked.
We want to model incompressible, fully developed turbulent flow without heat transfer between two infinite parallel plates with a spacing of 2 delta. Of course, because of the symmetry, we can model the problem in 2D and only simulate one half of the domain. And we also want to mimic the fully developed flow inside the channel. So we need to couple the inflow and outflow boundaries through cyclic or periodic boundary conditions. Therefore, there are a bunch of calculations that we need to do before starting the simulation. One of them is to calculate the source term that we need to give the software as the momentum source, which I've provided the formulation in the starting part of chapter 3, so you can easily do the calculations based on the value of R eta, the value of delta, and also the kinematic viscosity of the fluid. And also the other important parameter we need to evaluate is the parameter named G, which we need to calculate by assuming that the starting point in our y-normal direction is around y plus of unity. So based on the R eta value, you can calculate it. Of course, for this tutorial, I will use the values mentioned in table 3.1. Okay, so let's start the simulation. First, we need to do the pre-processing, and I've just started a new file, and also the license is set up, and it is ready to create the mesh. So as the first step, we need to expand the geometry in the simulation panel and right click on 3D CAD models and choose new. So here we see different planes, and we just need to choose the XY plane, right click on that and create sketch. I just want to create a rectangle. So from this create sketch entities, I choose create rectangle and put this point in the origin, and also the other point, the other diagonal point, I need to specify its x and y coordinates. So I click on that and specify the values for delta, which here are equal to 0.1 and also 0.1 for the y coordinate of the point on the diagonal. So I click OK, and the sketch is ready. Now we need to create a 3D geometry as in STAR-CCM Plus. All geometries are generated in 3 dimensions. So under features, you need to right click on your sketch and choose extrude. Here we need to just give a very small value. It could be small value like 0.01 meter. And then I just click OK, and I can now close the 3D CAD. After doing these steps, you can see 3D CAD model 1 under 3D CAD models, and we need to right click on that and choose new geometry part. Here we need to click OK, and now we can see body 1 under parts. And if I choose the geometry here from the create and open scenes, I can see the part that we have created so far. On the left panel, on the simulation panel, and under geometry and parts, I expand body 1. You can see that I have surfaces, and under surfaces I can see default one. I can see the default. So now we need to split this by patch. So right click on that and choose a split by patch, and you can see 6 different patches. And when you click on any of these patches, the patch gets highlighted, and then you can assign meaningful names to any of these patches. This is the inflow. This one is the outflow. Number 4 is the wall. Number 6, I name it as T. This one as S. Number 2 is the symmetry. I can't do the renaming here, I just need to do it here by right click on that and doing the renaming. So it is symmetry. Okay, so now we have splitted the patches and used meaningful names to note after this step we will need to come back and choose these patches. So it's a very good option to choose meaningful names so that we can easily identify any of these patches. Okay, so now under geometry parts, we need to right click on body 1 and assign parts to regions. So make sure that in the first drop down list you choose create a region for each part, and the second one create a boundary for each part surface. Click on the apply and then close. Now under parts you can see under geometry you can see operations, and we need to right click on that, choose new mesh and directed mesh, and we need to choose body 1 and click OK. I've added extra explanations about this form of meshing in the tutorial in the page 5 of chapter 3, so if you are interested you can further study this type of meshing. So now under operations we need to right click on directed mesh, click edit, and here we need to assign those surface and target patches that we need for this type of directed mesh, and that's why I was naming those patches as S and T. So here this is the T, so you click on this patch and add it to target. And on the other side you have the S, so right click on that and add to source. Now we need to right click on source meshes, and under new source mesh we need to click on patch mesh and select body 1 and choose OK. So here under create edit patch entities, we need to click on the auto populate feature edge with patch curves, and here we need to under mode we need to choose patch mode. So here please note that we want to create a mesh with fine resolution close to the wall. So that's why I was talking about calculating the parameter chi, which was the space at the starting point from the wall. So here first of all I choose this wall boundary condition while the type is constant, and I assign the value of mx that was given in table 1. It is equal to 5, and I just apply that, and then I choose the inflow. Here it is very important to use a grading close to the wall. So I need to change this type from constant to one side geometric, and then give the number of divisions, which was 40. And also I need to provide the spacing at the start, which was given in table 3.1 for this RETA, and here I put the value of this spacing at start, and click apply. So now we can see the grid here, and we can close this panel. Now we need to right click on mesh distributions and click new volume distribution and select body 1 and OK. Now we can close the panel for directed mesh, and under operations I can right click on this directed mesh and execute it. So when it is finished, it is important to convert this mesh to a 2D mesh. So from the menu you can easily convert it to 2D. Just make sure that you activate this tick close to the delete 3D regions after conversion and click OK. So now we need to set up the physics of the problem, and for this purpose under continua you have this physics 1 2D. So right click on this and select models. We have a bunch of options that we can choose here. Since I want to be able to choose the models myself, I just deactivate this auto select recommended models. For the time I choose steady. The problem is two-dimensional, it is already selected. As the material I choose liquid. I could also go with gas, because at the end of the day we are gonna give the density and also dynamic viscosity to the STAR-CCM. So it's okay that also choose gas, but here I'm going to go with liquid. And for the flow type, segregated flow, since we have incompressible flow, we choose constant density as the equation of state. And here we have the flow regime is turbulent. And then I need to choose the approach that I'm going to use for turbulent modeling, which is the RANS approach. And from the RANS models, I want to use k omega turbulence and SSD k omega. And since I have a fine near wall resolution, I will try to use a wall treatment that is compatible with that. So here I will choose low Y plus wall treatment. Please note that in this investigation, I will repeat the steps taken so far to create another case with a similar mesh but with high Y plus wall treatment so that we can see the impact of different wall treatment approaches. But for now, I'm just going with low Y plus treatment, and the problem is good to go. So I click close. Okay, now it is time to specify the thermophysical properties of the liquid. So expand the model, and under liquid we have water as the fluid here. So I'm gonna assign the values in table 1 for density. We had density equal to 1000 kilogram per meter cube, and for dynamic viscosity I will put the value and close the panel. So now the thermophysical properties are set, and it is time to start specifying the boundary conditions. It's a very important step in the process of simulation. So under continua physics 1 2D, we set the physics, and now we need to open the regions under body 1 2D. Here we can see the boundaries: inflow, outflow, symmetry, and wall. And please note that in Simcenter STAR-CCM Plus, the default boundary condition is wall. So we need to change these types for 3 of our boundaries. So here I'm gonna choose the inflow and outflow at the same time while holding the control key, and click edit. So here I'm gonna change the type to velocity inlet, and then in the physical under the same directory, I am gonna open this physical conditions and click on momentum source option, because as I said, we are gonna use this approach to mimic the fluid developed flow between the inflow and outflow. So here we need to choose this and just change this momentum source option from none to specified, and then under region body 1 2D physics value, we need to open this momentum source and enter the value that we calculated, and it was equal to tau wall over delta that you can easily calculate. And of course you need to apply it in the x direction. So it is all set, and now it is time to create interface from the inflow and outflow boundaries. So just again choose these two boundaries and right click and create interface. And then under interfaces you have the interface 1. So just choose this interface 1 and change the type to fully developed interface, and also the topology to periodic, and close. Okay, so the other geometry that we need to change its type is the symmetry. So we easily change it from wall to symmetry plane and close. Now our boundary conditions are okay. We need to specify some stopping criteria, because we need to limit the number of iterations that our simulation will go on. And here, so you need to expand stopping criteria, and under maximum steps you can just use a value. I'm going with 15,000. Our problem may be converged sooner than that, so I just use the large value just in case. So now it's time to run the simulation. So before doing any simulation, we need to initialize the problem. So here you can see this green flag here that you need to use for initialization, and then after that you can run the simulation by Control and R. So when your problem is converged, in this case we are going to use tables to extract our fields. So here the only post-processing approach that we are going to use is extracting the special distribution of any quantity of interest. For example, it could be the streamwise velocity. So please expand these tools, and under tables right click here, new table, and XYZ internal table. So by clicking on this, we are going to choose the scalar that we want to extract from our field. Here I'm going to extract the velocity in the x direction, so just choose this and send it to the box on the right and close. And also we need to specify the part, so we are going to extract this streamwise velocity field on region which includes body 1 2D, and make sure that you activate this data on vertices. So now it is good. And for unsteady problems, actually you can also specify then, for example, any time intervals or intervals based on the iterations that you need to extract data and also save to file. Here we just need to do this at the end of the simulation, since we are just dealing with steady RANS problem. So I need to close it, and when your simulation is done, so you need to click on extract and then export. So this is going to give you a file including x, y, and z coordinates and the streamwise velocity. And then of course you need to post-process it in any in-house code that you have, just like in a similar manner that you post-process your DNS data, and convert this u and y to y plus and to u plus and y plus respectively, so that we can plot this and compare it with the DNS data for RETA 180. Right. Now that I have post-processed the data, we can see the results of two RANS simulations against the DNS data for RETA 180 here in this plot. The blue line is QMG SSD with grid with fine near-wall resolution. And the wall treatment approach is low Y plus. So these two are compatible with each other. The grid is compatible with the wall treatment approach, and we can see a very good agreement between the RANS predicted results and also the DNS. But when we use high Y plus wall treatment for such a grid, we can see that the trend is not close to reality, and this shows the importance of choosing the correct wall treatment approach, and also special attention to the quality of mesh close to the wall. So this is it, and now you're ready to do the exercise, which is simulating incompressible turbulent flow in a similar channel at RETAU 395. So basically you need to set up the case with QMG system model and create a mesh having a fine near wall resolution and use the low Y plus wall treatment approach. But as the first step, please remember that you need to calculate the chip parameter compatible with that RE-tau and also the momentum source corresponding to this new friction Reynolds number. And after that, when your simulation is converted, you need to extract the data, calculate U plus and Y plus, and plot that and compare against the DNS data that you have for RETA 395. Okay, good luck and enjoy CFD simulation in STAR-CCM Plus.